Yes, thank you, Elisa. Yes, please interrupt me. I'm not sure I will see the chat, but I will hear you if you interrupt me. So the talk today is entitled Supercomputing of Large Earthquakes. And as you will see, I will also talk about some moderate sized earthquakes. I thank Chris and Elisa for inviting me. And I start with an introductory slide about the method that I'll be using for most of the geophysical results and the simulation results I will be presenting during the seminar. So you could summarize the method as data-fused dynamic rupture modeling of multi-fault earthquakes. And this flow chart is adapted from community papers led by Ruth Harris over the last decade or so, verifying different codes for these kind of dynamic rupture earthquake simulations. And what I'm plotting here, what I'm summarizing here is the input of this model. So that is geology. So for example, this is a multi-fault source model of the Kaikoura, New Zealand earthquake that we modeled. It happened in 2016, embedded in a 3D velocity model and accounting for high resolution topography and bathymetry. We also have to think about the loading of our faults, so initial fault stresses. We have to think about frictional constitutive relations that govern how these faults yield and slip co-seismically. We typically take from friction experiments. We have to discretize these simulations in terms of a computational mesh. We are solving the elastic wave equation, nonlinear coupled to friction laws on the prescribed fault interfaces. And we're generating output in the sense of synthetic observables. So that could be seismograms, that could be ground deformation, that can, for example, then serve as input for tsunami simulations. And of course, we're also seeing everything that happens in terms of earthquake physics on these fault systems. Some of the strengths of these simulations, if we do them indeed on the scale of actual multi-fault earthquakes, is that we can try and integrate and also interpret the full breadth of geophysical observations. And what I mean with that is that we can use these physics-based models to link between, for example, data from seismology, from geodesy, from the laboratory domain, from field studies, but also from longer term inferences, for example, about tectonic physics. We also can use modern approaches from data science, from applied math to make sense of the big data that we're producing. And we do need a fundamental understanding of continuum mechanics, rock mechanics, material science, and engineering to make sense of the simulations we're performing. And when I'm talking about, for the remainder of the seminar, about physics-based, what I mean is that we are solving for spontaneous dynamic earthquake rupture, breaking these faults as the nonlinear interaction of frictional failure and seismic wave propagation. So it's important to say that because these are not kinematic slip prescribed models or static models. And motivating for porting these kind of modeling techniques to actual earthquakes is that earthquake science is increasingly data rich. So this is, of course, a really nice example of a machine learning enhanced seismic catalog, showing us just how complex fault structures are also co-seismically activated, for example, throughout the central Italy sequence. We also have a lot of advances in distributed acoustic sensing and space geodesy, array techniques, and so on. And if you're looking at these data-driven approaches, we often see that we have complex multi-fault rupture characterizing moderate to large earthquakes. So this is an example you've seen before in the seminar series of inversion of the Nordsee earthquake, suggesting that there were two fault planes rupturing together. And we can use multiphysics forward modeling to synergistically integrate these data-driven methods that hint on these complex earthquake dynamics. And one example is led by Elisa, and she talked about that in an earlier seminar, where we are using these dynamic rupture simulations to probe the mechanic viability of some of the data-driven proposed source models. And we can also use data that is maybe not as obvious as strong ground motion seismograms. For example, fault zone width that can be compiled from aerial photographs. So here's an example of the fault zone width of the 1992 Landers earthquake. And we are using that observation to constrain a dynamic rupture earthquake simulation of the 1992 Landers earthquake, where we also not only model the slip on the fault, but also off-fault plastic deformation of the host rock. And we can map the plastic strain, nicely resembling accumulation of deformation around geometric fault complexity. And we even see strain accumulation forming or localizing, resampling fault structures that we didn't integrate in the models in the first place. So this here, this localized plastic strain, is a resampling a fault structure that was not prescribed in the earthquake simulation. We can also extend, constrain, and fuse data-driven approaches. And here is an example that links back to the FEAR seminar of František Galovic, who talked about Bayesian dynamic source inversion, so using dense strong ground motion recordings of the 2016 Amatrice earthquake to invert for the initial conditions that govern dynamic rupture models. And as part of this Bayesian dynamic source inversion, if you remember, we visited a million, or on the order of 1 billion forward models to come up with a preferred slip distribution, a preferred dynamic rupture model that matches the recordings at all of these stations best. But due to the computational demands, we were restricted to the relatively long period low frequency band of around 0.5 to 1 hertz, depending on the distance of this recordings to the fault. And now we've been interested in extending these kind of models to also better understand the broadband seismic wave field that's being recorded or generated. And what we did is that we have been taking the smooth preferred model from the data-driven dynamic source inversion, and we've combined that with small-scale fractal roughness. So with roughness, we mean statistical deviation from planarity of this fault surface. And we're also introducing heterogeneous D sub C, so heterogeneous fracture energy. We do dynamically correct for the additional roughness track that this kind of deviation of planarity poses for dynamic rupture simulation, and a little bit of an additional nucleation energy at the hypercenter. We're also adding topography, viscoelastic attenuation. And what we're seeing is a nice approach in trying to add bit by bit this additional complexities and trying to match the high frequency part of the seismic wave field. So what we are seeing here is just a simulation which shows the disturbance of the credence of the wavefronts caused by the roughness of the source and topography. And what we're plotting here are velocity and acceleration waveforms and Fourier amplitude spectra of the synthetics and of the observations. And in red, we have the rough fault model with topography. In green, we have the rough fault model without topography, and the reference model from the dynamic source inversion, which was relatively smooth, compared with observations. And what we observe is that adding this kind of physics-based complexity with, of course, a statistical distribution is really pushing the high-frequency content closer to observations. At many stations, we have some stations where this doesn't work, and these are the ones where we presumably have very strong side effects. So nonlinear soil response is not included in these forward models. We could also think about, or we're working towards using these models to inform probabilistic seismic hazard assessment and rapid earthquake response. And this animation is just one of a whole suite of dynamic rupture simulations that postdoc Bo Lee has been working on as part of the CHEESE project, where we've been setting up simulation suites for a fault system in North Iceland. So this is the Húsavík-Flatey fault system. And we were wondering which kind of complexity or which kind of complications we really need to include in these dynamic rupture models to make them useful to complement, for example, purely empirical attenuation relations or ground motion prediction equations. And we can vary fault system complexity from relatively simple geometries to more complex geometries that really map maybe surface expression of these faults. We can think about adding more complicated frictional behavior or off-fault plasticity. What Bo has been seeing is that we're really interested in a better understanding of the hazard, the probabilistic seismic hazard, for example, in the town of Húsavík. Models, for example, of the complexity of this model A shape here might be sufficient on the scale of running hundreds of these models to come up with better ground motion prediction equations. And I also want to point out that we can use these models to overcome observational limitations. And we have a recent preprint at ISOA that's led by James B. Miller, who's a postdoc at Scripps, trying to understand the dynamics of unlikely slip. And with unlikely slip, I mean large earthquakes on a low angle normal fault. I include that for Lauro, and I'm happy he's here. So this is a low-angle normal fault in Papua New Guinea, the Maui fault. And James has been working on that extensively during his PhD at UT Austin. And this is just a summary of all of the different geophysical and field observations that have been collected and trying to constrain the long-term, maybe seismic potential of this low-angle normal fault. And they've been concluding that indeed there has been potential large earthquakes hosted by this fault, even though with a relatively long recurrence rate outside of the instrumental coverage. And this is really interesting also from the dynamic point of view, because the understanding the mechanics, the long-term mechanics, but also the dynamics of such shallowly dipping normal faults is quite a challenge. They're apparently seeming to defy the laws of classical fault mechanics. And what we have been doing is that we've been using all of these different inferences, so that range from velocity stepping lab experiments to mapping and coral uplift mapping, and quite a large data set, everything besides actual earthquake recordings. And we've been translating that into the initial conditions for dynamic rupture earthquake simulations. So for example, we can think about the depth-dependent A/B distribution for rate and state-dependent friction law. And we can get, of course, the fault geometry in our 3D model. We have a 1D velocity model, which is visualized here. And what you see here, the side are the friction parameters that we're prescribing. And we're using here fast velocity weakening, so strong dynamic weakening friction law. And what we were interested in is to compare or to analyze 4 distinct loading scenarios. So we prescribing the frictional strength, the strength of the 1D velocity structure. We have, of course, bathymetry and topography data. We have a fault geometry model, but the loading is really, or varying the loading is really interesting in this case. So we have in the main part of the paper 4 different loading models. Model 1 which is our reference model, is producing the most plausible earthquake, uses Andersonian extension as inferred from the hanging wall. We have alternative model which uses back-rotated principal stresses as inferred paleopiezometrically from the exhumed footwall. We have a model which is really changing the initial loading, the tectonic loading, to be optimally inclined for slip on a shallowly dipping normal fault. And we have a 4th model, which is quite similar to the first one, but it reduces the static frictional strength in the upper 12-kilometer depth. And this is an overview of the earthquakes that we are describing for each of these 4 models. And we're seeing, interestingly, in the first model, if you're just looking at the slip contours in the uppermost row, we have this is a magnitude 7.8 earthquake, and we do see a little bit of surface slip, even though the upper part is velocity strengthening, and that is caused purely by variations of the fault geometry. So that part of the fault is a little bit steeper, which allows rupture dynamically to break through in the velocity strengthening part. If you're looking into the back-rotated, the footwall informed paleo stresses, which are even less optimally oriented for that kind of fault geometry, we basically have we are not succeeding to nucleate any dynamically spontaneously propagating earthquake. On the optimally inclined slip, we're producing an almost magnitude 8 earthquake, which features super shear rupture and an uplift of almost 12 meters, which is not shown here. So a very violent earthquake seems unlikely. And this model seems also plausible or interesting, which suppresses surface rupture. And we're concluding from that large low-angle normal faults in principle are dynamically viable under various stress conditions that include Andersonian extension. So they don't need to be interseismically critically stressed. And this is just an illustration of where these dynamic models behave a bit differently as static fault strength or slip tendency analysis, in which you really need all of the fault to be critically stressed, optimally oriented to host large earthquakes in that theory. And here we really need a small part to basically nucleate an earthquake, and then dynamically the propagation is not predetermined completely by, or doesn't require to be critically stressed. We see that shallow slip is limited by stabilizing effect of shallow fault geometry and velocity strengthening gouges. We also observe interesting dynamic effects that have been described before. So there's free surface interaction and a dip angle dependent clamping or unclamping effects if you have these thrust or normal fault dipping faults that are suppressing slip in this case. And these favorably inclined principal stresses may not be necessary for such fault systems to host large seismic slip. And why we chose this preferred model is that we've been comparing, just as a note, to coral uplift, where we've been seeing that we have a nice match of that model. Okay. The fourth model I showed, which had frictionally weak gouge analogies at the shallow parts, may limit the magnitude of interseismic shear stresses. It's interesting, but what we are currently studying is the effect of hanging walls play faults. So that was just a single fault earthquake, but if you're thinking about the effect of faults interacting in this kind of fault systems, especially the effect of hanging walls play faults, we can think about two effects. So during earthquakes, play faults may be activated and branching out and may port earthquake rupture propagation to the surface. And that's indeed what we're seeing. This is preliminary work by James, where we've been adding a splay fault dipping 45, 60, or 75 degrees. And we can observe how this is really suppressing shallow slip. And kind of because they're just more favorably oriented, the earthquake dynamically branches out, breaks preferably a display fault to the surface. And we've been also interested in the whole seismic cycle on these systems, and especially about potential creep that may relieve shallow interseismic stress on the detachment. And that's been proposed as part of the Keystone hypothesis, also motivated by the El Mayor Cucapa earthquake in California. And to model the whole seismic cycle, or CS models, so that is seismic sequences of earthquakes and aseismic slip for such systems, is challenging current computational methods, especially community codes. And at this point, I just want to highlight a recent preprint where we've been using this kind of setup as one of the demonstrators of a new method, which is allowing to have earthquake cycle simulations using a discontinuous Galerkin method on multiple faults, which are curved, for example, and which also allow to include heterogeneity. So for example, different materials in the hanging wall and in the foot wall. And these kind of methods do not widely exist that could allow you to really include this kind of natural complexity that we have on a dynamic scale. And the paper is a bit too technical to discuss today, but this is one of the simple showcases we include, where we have a low angle normal fault, and we have four splays at different distances to the main fault that are curved. And we're loading, this is a very simple setup, but we can already see that we have no earthquake here on the main fault, whereas the splays host a variable of rupture behavior, where we could maybe see some correlation between occurrence rate and the length of the splays and other interesting effects. Okay, there are certain, that brings me to challenges that we have in these kind of models. So first of all, earthquake source processes are ill-constrained and highly nonlinear. We have to decide which kind of physical processes we think are dominant for the question that we want to answer at hand, relevant or feasible to include at a given space-time scale we're modeling, and can be cost-wise justify to model them or to include them in our analysis. And the third challenge, where this last paper links to, how can we assimilate what we know and what we would like to include in modern software and hardware possibilities. So with software, I don't only mean like which coding language you would be you're preferring, but we're also thinking about which equations we're solving, which solvers are we using. And in terms of hardware, we are very interested in employing or making the biggest machines possible usable for earth sciences and bring our community really on these large supercomputers. And the motivation behind this is that if we are optimizing methods to be performing on these large supercomputers, this kind of optimization trickles down to also smaller scale models that, for example, a student is running on their laptop. It's the same processes, the same architecture that are used in the very large machines is the same that are using on the laptops or even that you're using in your mobile phone. If you're thinking about ARM processors, for example. Okay, here's another motivational slide of why optimization or thinking about optimal computational methods is worthwhile to do. So this is one of the most expensive simulations I could come up with to motivate that. That is 2 linked 100-second scenarios of the Ridgecrest earthquakes. And we're including here 3D subsurface structure, topography, viscoelastic attenuation, offward plasticity. And we want to say resolve up to 5 Hertz in the seismic wave field, and maybe also include a damage zone around the faults. And both of these simulations have to run together, since the Ridgecrest main shock should see the dynamic and the static stress changes that are caused by the Sears Valley foreshock. And if we're computing that, for example, on the SuperMOOC NG, that could take up to 9 hours on 400 nodes. So that's 170,000 CPU hours. So that's a very expensive simulation. If you're translating that in terms of monetary costs, and we're thinking about energy maybe being charged at 10 cents, that's $320. If you would be porting that simulation to a cloud service such as AWS, that would cost you $6,500 approximately. And translating that into energy, these are 2 barrels of oil equivalents, and into carbon or the dream of traveling for collaboration or for conferences, that would get you from London to Los Angeles. And as a side note, these numbers are of course machine specific. So there's a strong push towards more efficient, energy efficient supercomputers, and that could reduce these costs significantly. So also from an environmental point of view, this is really worthwhile to think about optimization. And this is just an image. I'm not going to talk about that scenario. I had previous talks about that, but of all the different observational data that you could use to constrain, inform, or to verify these forward models with. And I have a couple of summary slides about how we can think about balancing high performance computing and geophysics. We've been starting with that dynamic rupture simulations with a geophysics code, which was written in Fortran 90 MPI parallelized, and was reading and writing text files in serial. That means one processor is writing one file. For a large scale lander scenario, the biggest improvement was something that's called, I call assembler level DG kernels. What that basically means is that we're taking over the job of the compiler, and we're thinking about an optimal way how to unroll our loops. So this is something that every optimization flag in a code would be doing, but it's very difficult to do that for specifically those multiplications that we have to do in the code. And in terms of what this brings for the user, as you can see here in green, this is a 10 times faster time to solutions and allowed to have 100 times bigger problems. And that is basically often the difference between able to solve a problem because you can fit it into computational resources you have at hand, or not being able to do it. And then we're coming to the Sumatra scenario. That's something I will be talking about next. So scaling all of these methods up to large earthquakes. Largest earthquakes we know are happening on megathrust subduction zones. And there's one idea here that I really want to highlight, and that is called local time stepping. And it basically means that every element in the simulation is allowed to update their solution to the seismic wave equation at their own time step, and only talks to the other parts of the model when they really need to exchange information. And with all of this, this is a collaboration with especially the group of Michael Bader, the technical universities, so scientific computing experts and supercomputing centers. But what we can do is to run these multi-scale and multi-physics simulations for costing a couple of 100 to 1,000 CPU hours, and that makes it really feasible to explore a range of scenarios and even to do dynamic source inversion. In the next part of the talk, I would like to talk about a paper that's been published just a couple of days ago in Nature Geoscience, where we've been using these methods to identify key regional factors driving megatrust, earthquake, and tsunami dynamics. And we've been talking about stress, rigidity, and sediment strength. And we've been informing those inferences by 3D modeling of the 2004 Sumatra earthquake and tsunami. And this is a model here of the Sumatra megatrust we've been including, and also 3 splay faults that are part of the model. And this is just a visualization of the SLAP 2.0 model of all large megatrusts worldwide. And why do we want to model megatrust slip in 3D? So here's one motivation of a recent study where we've been modeling slow slip cycles in Mexico. And we've been showing that it's really interesting to account for 3D megatrust slab geometry and not be restricted to 2D. So Andrea Perez-Silva has been using models of slow slip cycles, no earthquake, just slow slip transients in the Guerrero seismic gap using a geometrically flexible 3D method. And the video that's been playing here is showing some of these transients she's been modeling. And we show that we can reproduce the source characteristics of 4 long-term SSEs as inferred from geodetic observations. And interesting is that the flat segment of the Cocos plate likely aids the large magnitudes and long recurrence duration of these specific slow slip cycle events, for example, compared to Cascadia. And this is the duration moment scaling that we're inferring from the models. And there's a recent study by Mathilde Radiguet who confirms that by new SSA geodetic observations in that region. So it's interesting to look at megatrust slip in 3D, for sure in the slow earthquake sense, but it's also interesting to do that on the co-seismic scale. So the first challenge to do that are the large space and time scale. So these are around 1,500 kilometers of faults that we're including. And we have to model those for about 5 minutes, 600 seconds of rupture plus the wave propagation, and then link it to tsunami models. So these are large and long simulations. And this is the computational domain we've been using. The main advantage is, as I've said before, local time stepping, but we've been also looking into really optimizing everything from the input, reading in the data, to writing it out and linking it to tsunami simulation. And these typical models that I show you now, they're running in about 5 hours on 16 nodes. And the second challenge from the geophysics point of view is how do we constrain the initial conditions and how do we verify these modeling outcomes, since these are forward models. These are not inversions. Given specifically megatrust structural complexity and scarce or asymmetric instrumental coverage. So we have a situation where we have global recordings for the 2004 Sumatra event and a variety of data that has been used to infer something about the source. All of these data has revealed a long strike complexity. And it also has been really challenging to come up with source models that match all of the data at the same time, specifically the earthquake and the tsunami associated data. So these are just some of the examples. This is our GPS data that we could be using. This is the long strike moment release variation. So this is latitude, this is the moment rate released. You can see this kind of variation along strike, and here are radiated T waves. This is just a recent summary of data-driven earthquake models. This is a paper from tsunami modelers, and they've been just plotting like different kinematic or other data-driven source descriptions of the 2004 event. You can see quite a large variation. And if those models are then used to model tsunamis, because we also see a large variation in the tsunami, even though tsunamis do act as a low pass filter in terms of smaller scale complexity. So data-driven earthquake models vary, and they may not match all observations at the same time equally well. And this motivation for building a physics-based model and try to see if we can identify which factors are actually most important to include or might be driving the dynamics of these large events. And what we're doing is we're including first, if you're thinking back to our flowchart, think first about the geology. And we've been constructing our model by including the curved megathrust based on slab to zero and intersecting splay faults merged with high resolution bathymetry. We do omit in this study smaller scale geometry or heterogeneities or asperities. We are allowing for we're allowing for potential seaward extension of the plate interface because we were interested in the trade-offs of slip to the trench versus maybe splay fault activation, and the 3D subsurface model adapted from crust 1.0 and local tomography. And this is here an interesting study that we've been using to construct the seaward extension of the plate interface by Dean et al., which showed this high trench sediment velocities and hypothesize about the seaward extension of the plate interface north of the rupture boundary at least. We do also include a lower velocity subduction channel, which features strong rigidity variation. So our megathrust is embedded in a channel which accounts for this globally inferred variations of rigidity with depth. And what we're plotting here in black is rigidity with depth based on Thorne-Lay study in 2012. And SR219 is short for this paper by Salares and Ranero. And in comparison, these dotted lines would be the PREM model. So where we don't have this reduction of rigidity at shallow depths. The incoming sediment can be of variable strength to account for accretion, mechanical compaction, and mineral dehydration that promote litifaction. So we have alternative models that have stronger or weaker sediments. And we do account for off-fault plastic deformation of these near-trench sediments by coupling the bulk cohesion. So that's a parameter that's tricky to constrain to effective vertical stresses. And our model is summarized here. It's a complicated diagram, but what we show is depth, cohesion, and closeness to failure. And the blue lines, they're showing you the cohesion values. And these red lines, they're basically showing how close to failure our sediments are at different cross sections along the megathrust for the weak sediments and the strong sediments and the reference scenario. Now, we want to think about how we can constrain the strength and the initial stresses of this model. And what we do is that we align stress inversion and geodetic observations in choosing the orientation of SH max. And we also account for the observationally inferred clockwise rotation of SH max along strike. And we also account for non-Andersonian initial stress fields, so we allow for a plunge of the loading of this fault system, a shallowly plunging maximum compressive stress. And what we are visualizing here is the Harderbeck 2012 inferences in terms of SH max in our study, and also the plunge that we are inferring.
Can I interrupt? It's Chris, sorry.
Sure.
Just one slide back, I guess it was. When you show us, maybe just one before this, when you show us the stress variations as a function of depth, this is the coefficient of friction on the top?
Here?
Yeah.
Yeah, so this is this is not what's happening on the fault, but really how we describe the strength of the off-fault bulk in these models of the sediments. So this is CF is closeness to failure. So that's a quantity that's been established, I guess, by Templeton and Rice. And it's just if you're at 1, you're basically at failure.
Yeah, okay, sorry. Yeah, misinterpreted. Yeah, I see. So
yes.
Closest to failure. I see. So then by the time you reach, because the strong sediment, you're nowhere near close until you get down to about 40 kilometers or so.
Right. The strong sediments, they're never close to failure, right? They're never reaching 1.
Gotcha. Okay, yeah, thank you.
Yeah. Okay. Okay. And at this point, I would like to link back to 2 earlier studies where we've been coming up with only 4 four initial parameters that can describe the initial loading and strength of these multifold dynamic rupture scenarios in a coherent way. And there's specifically a model of the Kaikoura earthquake, and there's also a study of the Pohang earthquake. So that's Palgonadi and Thomas Ulrich in 2019 and 2020. And we've been developing the static way of how to constrain the initial stress by basically exposing our complicated or realistic fault geometry to a regional loading that's only allowed really to vary regionally. And we're only running a few dynamic rupture models to basically constrain loading variations with depth. And how this can look like in practice is visualized here for, this is the fault geometry of the Palu earthquake where we applied the same approach. So this is something you could think about as a dynamic slip tendency analysis. So we're basically exposing this fault system to varying SH max, so varying angles of the maximum compressive stress. And we're checking something that we call the relative pre-stress ratio. And that is a measure for the ratio of the strength drop and the stress drop. So it's a dynamic strength of these faults. And we're also checking for an optimal rake that this kind of loading would infer. And this is something that we can compared to kinematic inferences of rake, so simple rake inferences as strike slip earthquakes or thrust or normal faulting. And this has been proven really useful to avoid having to run a large amount of forward models to explore the parameter space, because we can basically, we're also adding the fluid pressure ratio as kind of the fourth parameter that is scaling the gradient of the normal stress with depth. But we can really nicely see that there will be only a few of these models which are actually dynamically viable under these kind of relatively strict framework. And one of the important assumptions that we are having in this framework is that we include fast velocity weakening friction. It's important to balance realistic slip, realistic stress drops, and at the same time have the possibility of rupture jumping from segment to segment. And we're also thinking that these faults are statically strong and dynamically weak. So there's a couple of assumptions that go into this framework, but it boils down to only a few parameters that we have to constrain. Now, on the scale of the Sumatra earthquake, we can really nicely come up with optimal starting parameters for these models when we analyze the trade-off between fault stress drop and breakdown strength drop. And what we find is that we do need statically strong faults. We can constrain the friction drop from data, and specifically we use the rotation of the inferred stress tensors on CFM solutions before and after the event. We do need high, so nearly the static fluid pressure, and linearly depth-dependent effective confining stress to reproduce the observations we have at hand. And important is that the absolute variations in the pre-stress magnitude are small. So what we see here is the shear over the effective normal stress. And this is the same plot, but zoomed in between 0.43 and 0.47. So these are small variations. And it also shows you that the subduction interface in our model is nearly always optimally oriented. And next, we also account for an amplitude of deviatoric stresses varying along strike, and we modulate them by the tectonic convergence rate and the log variation of that convergence rate. And for that, we're just falling back to simple Euler pole analysis, which is basically scaling our R. So remember, this is our effective fault strength, which I write out here. So this is often called the relative pre-stress ratio, which is scaling friction strength drop and stress drop, and it's modulated by the magnitude of the convergence rate. Then we follow Jean Hardebeck's work, thinking about co-seismic rotation, and she's been finding for this event that there was a significant principal stress rotation that implies pre-stress and stress drop are basically of the same order. And this can also lead to interesting effects, such as a sudden switch of orientation of the principal axis of stress, as we've been seeing, for example, after the Tohoku earthquake, where we suddenly see a lot of normal faulting events following large megathrust earthquakes. So that is maybe something that is not only true for the 2004 Sumatra event. And we can use this information to constrain the level of the initial to the residual stress in our models. So we're fixing static frictional strength to 0.6 following our core assumption that faults are statically strong. And we fixing our R0 based on the tectonic plate convergence rate. And then we can take the ratio of the residual shear traction over the pre-stress from observations. And then we can infer an effective dynamic friction coefficient for these models, which is here 0.2. So that basically allows us to observationally constrain the initial conditions that we need for these models. And it's interesting because recent studies have been trying to also get these co-seismic stress rotations for crustal earthquakes based on optical pixel correlation. So that would be really interesting to try that for other events. Okay, we assume here linear slip weakening friction, which is sufficient for these large earthquakes where we don't account for really actual multi-fault rupture cascading, a large friction energy leading to wide process zones or wide slip pulse. And we can model the spontaneous arrest of the earthquake as well. Now, we've been using observations to come up with the initial conditions of this model. We can also use observations to verify independently the outcomes of the model. And this is how snapshots of the earthquake dynamics look like. We see already some interesting things. For example, this boomerang-shaped megathrust slip pulse consisting of multiple rupture fronts. So with boomerang-shaped, I mean the slower rupture speed at the shallow parts, faster rupture speed at depth, and then again slower at close to the seismogenic depth. In this model, all splay faults rupture, and we can compare it, for example, to a 5-point CMT model that is here worked by Victor Tsai, and we have an excellent agreement. This variation in loading and in convergence really constrain also how the rupture stops. So this is not a forced stop of the rupture, but it spontaneously stops in the north and also in the south. We can also compare against crown deformation, and here's a comparison of the modeled and observational crown displacements. We have the synthetics in blue and observations in orange. And we also see these interesting splay fault signatures here in the vertical uplifts. This is a comparison in terms of fault slip of our model. You see this kind of slip segmentation with these patches forming here, but the model is relatively smooth since we are not prescribing any smaller scale heterogeneities here and resembling kinematic models. In terms of teleseismics and acoustics, we can look at moment rate release. In blue is the base scenario to 600 seconds. These are a couple of published inferences. Rupture speed at different depths. It compares relatively well in terms of uncertainties. We can also translate these models into a couple of sources using, for example, instasize to produce teleseismics at various stations in further distances. And so this would be the synthetics that we're producing based on an axisymmetric global seismic wave propagation code. So this is not the full complex multiphysics forward model here. Now, what's interesting is if we're also trying to match tsunami data. And this is where the role of the sediments becomes really apparent. So this is if we are changing the sediment strength according to that plot that Chris just asked me about, to stronger sediments or weaker sediments, we see kind of a variation in slip. So if you have stronger sediments, you see more slip to the trench. If you have weaker sediments, slip is pushed away from the trench. If you're looking at that in terms of off-fault deformation, you have a lot of deformation in the sediments in the weak sediment scenario. Now, interestingly, these alternative scenarios are not distinguishable in any of the other observational verifications that I just showed you in terms of GPS, in terms of fault slip. You can argue if you would be able to resolve that, likely not, in terms of teleseismics or acoustics. But in the tsunami data, they make a huge difference. If we are using this dynamic source scenario in GeoClaw, and that's in that case to model the tsunami, we actually see quite a large difference. And what we show here also in the base scenario, the weaker sediment model is rupturing much longer, almost to 800 seconds, but that is something that's also tricky to resolve. So this is following a workflow we've been developing in, over the last years, where we've been linking these models and use them as input for tsunami models. And this is the plot from the paper, where we basically shown that dynamically sourced tsunami synthetics are very sensitive to the magnitude of fault slip to the trench or the sediment strength in these models. And in green, you have really these high overshoots of the amplitudes in terms of including weaker sediments in these models. And for stronger sediments, there's not such a large difference here, but there's other observables that don't match as well. For example, that's why there's a little zooming window here. There's an interesting double peak that's been analyzed before. That is more tricky to capture. And these are how these tsunami models look like. So all three scenarios capture the pronounced two-peak characteristic of the first tsunami wave. That's actually something that is really a dynamic effect. However, overall, the base and the stronger scenario fit much better. And this reference model is really more consistent with the inference of lithified sediments in this region. So what do we learn from this? And I wanted to show one plot from the supplement of the paper here too. So this would be the geodetic fit if we don't account for the long arc pre-stress modulations. If we would just have the same relative fault strength all along strike of the megathrust here. It's just basically completely overshooting in the upper part. So there's a large sensitivity to all of these three factors that we've been identifying. And I think it's interesting to stress the importance of regional scale structural heterogeneity and geometry to decipher megathrust hazards. And the dominant regional factors are tectonic stress, rigidity, and sediments near the fault. And we can also use this model to reconcile seismic, geodetic, geologic, and tsunami observations. And that's something that's been interested in also in generic dynamic rupture models. But we showed in this data constraint setting that there are these trade-offs between slip to the trench, bulk yielding of the wedge, and splay faulting don't have a huge effect here, but that is part of another study. And what we could do next, I have a couple of slides about that. We've been looking into stepping away from this linking, which is kind of cumbersome for a couple of reasons, by trying to develop 3D fully coupled earthquake tsunami models. And this is a paper that's been published in the Supercomputing conference this year for the 2018 Palu Sulawesi earthquake and tsunami. And the interest here is to allow 3D solid fluid coupling. So we're not only solving the dynamic rupture problem, but we are also looking into acoustic wave equation and gravity waves. And gravity waves can be in a neat way described, but perturbations of about an equilibrium state of compressible inviscid ocean. This is basically just a boundary condition in our model. Okay, and I should walk you through that. This is the earthquake model. So that was published earlier. One of the key points is that we've been showing that also co-seismic uplift can have a crucial impact on the local tsunami caused by strike slip movement along this geometrically complex fault system that also includes some normal faulting and combined with this complicated bathtub-like geometry. But if we are sticking with this linking approach, there's a couple of assumptions that we're doing, and that is a plot by Lauren Abrahams, where she's comparing all these different coupling techniques and analyzing them in great detail. And what we've been interested in here now is really this fully coupled method, and Sisal is the code that we've been using. And we're doing that because we want to not omit tsunami dispersion. So tsunami waves are dispersive, acoustic waves, momentum transfer, and in general, the complexity of source effects during tsunami generation. And the models that we've been running resolve up to 30 Hertz. There's a couple of numbers. It's large and it scales very well. So it's a computing challenge to make that work. Skipping through that maybe for now. But what's interesting really is if you're looking at this simulation, this is here the fully coupled model of the tsunami. And this is the traditionally shallow water equation-based tsunami model. And we're basically seeing quite a difference that is a little bit unexpected, because in simple models, we actually don't see any difference besides acoustic waves being generated. And we do think that we see here really the effect of non-hydrostatic response under this complex geometry of Paolo Bay, affecting the smoothness of these tsunami wave fronts. And that has important implications if you're thinking about the Tonga eruption, but also if you're thinking about early warning based on acoustic waves or based on ocean pressure sensors that would be relying on accurate using of the recorded pressure or acoustic waves for tsunami early warning. Okay, and to end, there's a couple of ideas what we could do in the future, given we invest into, well, we continue to develop new methods. And one of the things I want to point out is that there's a large movement towards developing methods that do not require you to come up with a specific geometry that you want to model, but that allow, for example, for adaptive meshing, or that would allow for curvilinear approaches where implementing, for example, complicated topography is part of the simulation itself. And we see it's coming. Yeah, one of the examples I wanted to show, and one of the shortcomings maybe of the models I showed so far, is that in these dynamic simulations, we're prescribing how earthquakes nucleate. And there's an interesting study we've been involved in, maybe for this audience, is trying to better understand earthquakes maybe nucleating or being completely constrained to fault damage zones, modeling them as a cascading rupture in this multi-scale fracture network. And that's work led by Kadek Palgunadi at KAUST, collaboration with Dimitri Garagash and Martin May. And the question is why, how can we develop a physics-based understanding of earthquake nucleation and maybe also precursors, and why we struggle to observe those. And what we've been setting up is dynamic rupture simulations on 850 multi-scale fractures, and that's an exploded view here. These fractures are surrounding a main fault, as you can see here. This is a listric fault plane. And all of these 850 fractures are scaling based on statistical relations stemming from the reservoir fracturing community, so really from the hydraulic fracturing community. And this is here, these snapshots are one example where the fractures are favorable oriented and the main fault is poorly oriented. And as you can see, the fractures are hosting self-sustained cascading rupture. So in yellow means they were slipping, they hosted some slip during the simulation, but they failed to activate the main fault. And if you're looking at these at this model from a distance, we basically see a pure strike slip moment tensor resembling that. But if you would be looking at that in terms of fracture mechanics, you could think about this as a, I don't know, a mode 4 like rupture. So there's it's basically really breaking all of these faults separately. And one important ingredient that we had to develop to model not only large earthquakes, but small earthquakes is to think about how we can scale the frictional parameters, especially fracture energy, with rupture size in these models. And all of these, or why the talk is entitled maybe large earthquakes, is that the friction laws that we have and these frameworks that we develop work nicely to match observations of large earthquakes. If you're thinking about modeling small earthquakes, cascades of fractures, for example, or maybe small magnitude 1, magnitude 2 or smaller induced earthquakes, we do have to change fracture energy in a certain sense, also in these dynamic models. And what we're doing here is that we are assuming that fracture energy is correlated with fracture size or slip, depending how you want to look at it. And this is the animation of the slip evolving through the fracture network without activating the main fault. And this is my last topic, where we've also been thinking about not prescribing these fractures, but modeling how they grow. And there's really nice work by the group of Harshabat. But in difference maybe to here, we've been interested in also exploring if we can use different equations, if you can think about different mathematical frameworks to better understand the fractures of, or the fractures or dynamic rupture in diffuse fracture zones. And the model I show here can maybe play that again. These are mesoscopic shear cracks that are spontaneously generated by a dynamic rupture in this diffuse fault zone here. And what's interesting is that we are seeing spontaneous formation of conjugate shear faulting around two favorable orientations that kind of seem to resemble recent high resolution imaging of earthquakes. And we also see interesting differences to purely planar or collapsing all of the physics that we're interested in into the fault interface in terms of earthquake characteristics. We have a larger stress drop. And for example, it's more difficult to generate super shear transitions. So I said we're interested in using different equations, and this is a summary of the mathematical formulation that we've been using here. That's going back to Godunov and Rumensky to the 70s. And the idea is to have a thermodynamically compatible description of nonlinear elastoplasticity, damage, and also Newtonian flows. And we start with conservation of mass, momentum, and energy, and it's a hyperbolic PDE, so similar maybe to the wave equation. But what's important is that this is a mathematical system which needs to be, again, constrained by, in this case, laboratory studies that give us, for example, stress strain curves of how the rheology of the deformation should perform. So what we've been doing in the models is that we've been coupling one model for damage, so this for allowing for the shear failure of the bulk material, with tuning the same model towards resampling, for example, linear slip weakening friction in the fault zone to model the simulation that I just showed you before. What's interesting is that the same frameworks, you can think about it, something that maybe resembles phase field approaches, so diffuse deformation approaches, would also allow to investigate the transition to fluids. And that is something that we're currently very interested in. Okay, and I think with this slide, I should be finished. Oh, I go to the end at least. And I want to summarize that I showed 3D physics-based dynamic rupture models that provide mechanical viable insight into physical conditions that govern earthquake dynamics. For example, or this kind of the challenge in terms of scales on megatrust fault systems for large earthquakes. We can include observational constraints. We can also unify them, sometimes challenging, or probe different proposed models for dynamic plausibility. We can bridge scales. And we are just at the interface, or at this point in time where we can go beyond scenario-based analysis. And we're thinking about Bayesian approaches, UQ, hybrid HPC, and machine learning modeling. But this is work in progress. I can hopefully talk about the next time. And there's some of the references here. There were some AGU references too. So I think all of these talks and posters are still online. That's why I included them. And with this, I hope for many questions in the discussion. Thanks for listening.
Thanks, Alice. Please, everybody unmute. And thanks, Alice, for this huge amount of work. Very nice talk.
Nice.